HVAC 360 is brought to you today by Professor Fenster's Magic Smoke. Has your computer been running slow? New equipment not operating the way it should? Maybe it's just running low on the stuff that makes all electronics work. What's that, you ask? Electricity? No! It's Magic Smoke! You may never have known what it was, but if you've ever seen a device die with a pop, sizzle, and a release of plume of opaque gas, then you've seen Magic Smoke. Top off your electronics today with a 6-ounce can of Professor Fenster's Magic Smoke. Hey, what's up? Welcome back. This is episode number 102. Matt Nelson here, your host for HVAC 360, helping you be the best and the brightest in the field of HVAC. How do we go about doing that? Well, we do that by sharing lessons learned that I bring back from the field and talking to industry experts that fill your ear holes full of HVAC knowledge. But we don't really stop there. We also have we double down on HVAC goodness. If you go over to HVAC360.com, sign up for my mailing list there, and you will join the growing community of HVAC enthusiasts just like you. So, what's up for this week? I'm super excited. We get to talk with Jason Geagan, who is from the U.S. Draft Company. I met him the other day at a local ASHRAE meeting, and his presentation on boiler venting was excellent. There's a number of things that he mentioned that I had forgotten. There's also a couple of things that he mentioned that I never thought of. So I thought I'd get him on the show and talk to him a little bit about boiler venting since we're getting into the colder months. So, without further ado, let's cut to the tape. All right, today we're talking with Jason Geagan, who's the national sales manager for U.S. Draft Company. How you doing today, Jason?
Good. How are you, sir?
I am doing fantastic. So, U.S. Draft, tell us a little bit about who they are and what they do.
Sure. U.S. Draft is a mechanical draft manufacturer out of Fort Worth, Texas. We manufacture fans, overdraft dampers, and all of the controls and accessories that go along with it to maintain proper draft, proper combustion air for any type of gas-fired appliances.
So I guess we're going to talk a little bit about boiler venting today. Is improper venting really a big deal?
It probably is the biggest deal, and it's the most overlooked issue in the boiler room. And throughout this conversation, we'll use the word boiler, but it really applies to domestic water heaters, pool heaters, even gas furnaces or unit heaters. And the problem is that it is something that is tough to diagnose without the proper tools, and it's tough to overcome without looking at some other forms like mechanical draft. And the reason for it is improper venting can affect your combustion, or it will affect your combustion, which also then affects your thermal efficiencies, and it deteriorates parts much more quickly, whether it's your burner or your combustion chamber. And unfortunately, it's always the last thing that's thought of. So it's kind of put together, with extra fittings and extra tees and extra pipe that may or may not be necessary and may or may not allow that boiler or appliance to fire properly.
So now, I guess when we talk about venting, I know there's if you're familiar with it at all, you know that there is basically 4 classifications for venting, and there's a typical diagram that goes along with that. If you take like a cross, and along the x-axis you have on the left side you have the negative, and on the right side you have the positive pressure within the vent. And then on the y-axis, we have the condensing condensing on the condensing on the bottom to to non-condensing on the top.
Right.
So I guess can you describe some of the when you look at that, what's important about that? What should people understand when they look at that diagram?
Sure. So that's the ANSI vending categorization chart that you're referencing there, and that determines what type of material. That determines what the boiler is categorized as, which then determines the type of venting material. So you talked about the vertical. The Y is the condensing and non-condensing. The biggest thing that's maybe misunderstood about that is that people think, well, I have a non-condensing boiler, so it's probably on the top side of that chart. This has nothing to do with the boiler's capabilities of condensing. There are non-condensing boilers that would be considered a condensing boiler when it comes to venting. Typically, that 85 plus efficiency is kind of that break point where it goes from a non-condensing system to a condensing system on the venting side. So category 1 would be negative pressure non-condensing. So where negative pressure meaning that Mother Nature is pulling those flue products out, right? There's a lot of limitations, and NFPA gives an entire chapter on how to vent category 1 appliances. Those are standard B vent UL 441. Categories 2, 3, and 4, for various reasons, all use UL 1738 special gas vent. It's a listing for the UL standard listing for pressurized and or corrosive conditions like condensing vent systems. So categories 2 would be negative condensing, category 3 being positive non-condensing, category 4 being condensing and positive.
Now, I guess, and positive, positive, negative, when you talked about the negative side, obviously that is the atmospheric, the Mother Nature's drafting with that. And obviously on the other side, you have the positive, and that's where you have a fan on the combustion appliance that's actually pushing air up the stack. Correct?
That's correct. So there's many of the boilers manufactured today have a fan built into the unit that helps with the combustion process. And that fan is capable of then pushing those flue products up to anywhere from 30 to 100 feet, depending on the manufacturer. Once you exceed those limits, that's where mechanical draft comes into play. But it also kind of applies to mechanical draft fans. So if you're using an inline fan, anything on the inlet side of that fan would be a negative pressure. Anything on the outlet side would be a positive pressure. So if you were to use an inline fan, which I think we'll talk about in a bit, but if you were to use an inline fan on a category 1, for instance, the system itself would be negative, but once you get to that fan, everything past that is now positive. So you have to make sure that you're looking at that when you're sizing up your systems.
And I think it's important to point out too that when you look at this diagram, you have a lot of the older style, water heaters, boilers. They are the classic category 1 type venting. And when you look at some of the newer stuff that has a power vent on it, that's going to be more efficient, condensing boilers, that's going to be more of your 4 categories. So they're kind of opposite quadrants of this diagram.
Correct. And as you were mentioning, the newer style, prepackaged sealed combustion, and I guess the kind of sidebar, that's how you get some of those efficiencies, is that you're controlling the combustion process. If you have a big draft hood atmospheric boiler category 1, you can't control the air to gas mixture, right? You just get the air that's given and you set up your gas for whatever it is. When you get into these sealed combustion units, that's where you can really dial in your air to gas mixture. So now you can start to tighten up your combustion efficiencies. And depending on the application, whether it's vertical or horizontal, how much horizontal versus how much vertical, that determines whether it's going to be a positive or a negative. It could be positive at the outlet, but then go negative in the vertical. So it really does depend. And that's why 2 and 4 both share the same listing, so that you can use the same material, no matter which case it is.
Now, I guess to kind of go over once again, when we talk about the non-condensing in the stack and the condensing in the stack, I mean, how does, because as an engineer, you look at a boiler and you go, right away, okay, it's a condensing, non-condensing. You could probably identify that. So you're like, oh, this should be pretty easy. But it's in the stack. So how does that, how do you determine, if you're going to be kind of, I guess, in one, how can you determine whether or not that's going to change your category?
Sure. So by code, the boiler manufacturer has to list what categories they are listed under. Many boilers that are category 1 that are sealed combustion can also be category 3. Most boilers that are above that 85% are going to be either category 2 or 4. So it really comes down to the boiler manufacturer, and when you're designing your system, working with that manufacturer to say, we are installing, brand X boiler, and we're going out this much and up that much, and kind of giving a general layout. And most boiler manufacturers or their representatives can assist you with that. And that's why it's helpful, the fact that a near condensing or condensing boiler, again, 85, 86% up, the material doesn't change. Where it gets tricky is knowing that if I'm, people look at it and say, well, I'm terminating vertical, so it must be a category 2 because I'm getting natural lift. If you're doing a 70-foot horizontal run and a 10-foot vertical, that is never going to be negative. There's no chance of that being negative just based on the math. So now you're getting into category 4, and then you have to start looking at how much distance can that category 4 appliance run. So from a material standpoint, on the near condensing or condensing, it's actually fairly easy compared to the non-condensing boilers, because that's where, and typically those are your horizontal stage fired, 82 to 84%, that are category 1 naturally. You'll put a barometric, you go vertical, couple stories, and it works just like a draft head appliance, just a little bit more efficient. Where it goes category 3 is in your sidewall applications or in some direct vent applications, where the boiler is now doing the grunt of the work, right? That internal fan is starting to give some of that push back to the vent, or push to the vent material. So now you're going to go positive, and that's where it goes from being a V-vent application to a special gas vent application.
So let's get into the materials a little bit. You've seen a lot of materials out there. So Sure. Just tell us about the materials that typical boiler venting would have. Sure.
So category 1 is, as I mentioned, UL 441 is the listing, the official listing. Standard double wall B vent. It's available at most hardware stores around the country. Every supply house typically stocks, a B vent style double wall galvanized or gal aluminum blend. 2, 3, and 4. The misconception is that if it's a condensing application, you have to use AL294C, which is an alloy that is used by manufacturers for UL 1738. But it's not the only listing. UL 1738 doesn't actually mention anything about materials, other than they must meet certain criteria for corrosion. And so many vent manufacturers have gone to 316L stainless steel, 444 stainless steel. Even there's a plastic manufacturer, or several manufacturers that are using a plastic blend called polypropylene, which goes through the same testing that the stainless steel vent pipe manufacturers go through for corrosion and pressure. So there's a lot of different options. My advice is always, no matter what you're doing, just make sure it's a UL listed product. Many vent manufacturers are starting to offer or allow for PVC and CPVC. As a venting guy, I'm not a fan of putting flue products into a product that's not listed for that application. There's no way that they can meet the 1738 requirements, and so therefore they don't even try. And many plastic pipe manufacturers don't even encourage using their products for that application. So there's just a lot of limitations to PVC and CPVC that haven't really people haven't really dug into enough, in my mind, to do that. So my advice is always use a UL listed product, even if the boiler manufacturer says, hey, we can use PVC or CPVC. There's a lot of things you can do in life that you shouldn't. So that's one of those in my mind.
So, and that's, to me that I see, a lot of the, I just see it everywhere. From, even my own home to commercial applications, that they'll run, the vent piping, in plastic, PVC or CBVC. So that seems, I guess it's so easy to cut, so easy to handle.
Sure.
You can just buy it off the shelf or whatever, but it's not, like you said, I guess it's not UL listed. So that creates a lot of problems.
I'm sorry.
No.
If you don't mind me, just real quick, the problem with PVC or some of the struggles is there's temperature ratings on the pipe. They have a quote unquote melting point to where PVC is at about 155 at atmosphere, CPVC about 190 at atmosphere. And so since UL is not going to list the vent pipe, they then put it back on the boiler manufacturer, and the boiler manufacturer then puts limitations on the boiler when using those products, typically some kind of a temperature sensor or temperature limiter on the flue, that if you start to exceed the temperature limit of that material, it will either derate or shut off the boiler. So now, when it's put in its proper application, though it's in my mind still not correct because it's not UL listed, PVC and CPVC can be used and work okay. Where you get into these struggles is they just look at it and say, well, the boiler can vent with PVC, so let's use that. But what they don't look at is their water temperature affects your flue temperature. So if your water temperatures are going to exceed, say, 110 degrees on your return, you're probably going to overheat that stack, which then will limit or shut off the boiler. So there's a lot of these, again, things you can do that you shouldn't. And to me, if you want to cover yourself on all cases, in all systems, under all conditions, use a UL listed product.
Now, I guess what is when you say that there's going to be a setting that limits the temperatures, is that something that is going to be set in the field or set at the factory?
No, that's typically a factory set sensor, and each boiler manufacturer, depending on what they've gotten approved. Again, they've had to go through testing to do this through their categorization listings. So they'll set that for, typically it's anywhere from 135 to 150 degrees for PVC. Some people that don't offer PVC that will allow CPVC, that might be about 180 degrees. It's just underneath whatever they feel comfortable with. There is no, I don't believe, and maybe this has changed and I'll have to dig into it, but I don't believe there's an actual requirement temperature setting. And it doesn't require you to shut the boiler off. It just requires you to lower your firing rate or lower the temperature of the boiler. In order to do that, you have to lower the firing rate. So it really, it's kind of that, whatever the boiler manufacturer feels is safe. And so it's all factory set typically.
Okay. So now I guess talking about the different sizes, obviously, PVC, CPVC, you see it a lot in the smaller 3-inch, 4-inch applications. You don't see a lot of it in larger applications. Is there a reason for that?
Well, cost. When you get into 8, 10, even 12-inch PVC, it's not cheap. It's as long as you're using Schedule 40, which is another quick sidebar. Foam core should never, ever be used for anything when it comes to heat, right? Though I've seen it tried, but typically they want you either in Schedule 40 or Schedule AB PVC or CPVC. And when you start getting into those true heavier plastics, the cost of the pipe itself can be pricey. The cost of handling it is now, again, 10-inch PVC in 10-foot lengths is not light. So now you're getting much more manpower to handle that. So once you get above that, again, depending on the market, depending on cost of commodities and such, but that 6 to 8-inch range, it's probably just as cost effective to use stainless steel or polypropylene. Polypropylene is a real good alternative in that size. And then 10, 12-inch, again, you're starting to get that crossover from poly to stainless, where PVC is actually the least cost effective. And then you get into the fact that you should be using high temp glues and primers. So then the cost just continues to go up from there.
So I guess the moral of the story here is read the manufacturer's information on the installation, because I'm a commissioning guy, so I know that contractors, because of schedule constraints and things like that, or just because they don't know and they did it on the last job and they think they can do it on this job, they might substitute materials. They might put in the wrong thing. So make sure you check that out when you're out in the field.
Absolutely. And if you were to say, for me, if you want to cover yourself under all circumstances for all systems, require UL 1738 for your venting. It gives you a lot less limitations. That's what all of the sizing charts and everything that the different manufacturers use. PVC doesn't even have K values listed. I mean, there's a lot of things about PVC and CPVC that just create a lot of gray area to me. And when you're dealing with a deadly flue gases, because obviously there are deadly gases in your flue gas, that it's just not something that I personally would want to mess with from a liability standpoint or from an operational standpoint.
Sure. So I guess, can you tell me the difference now? I mean, we've gone through the materials. What, as far as installing it and putting it in, the difference between NFPA 54 and the ASHRAE fundamentals. What's the difference between those two?
Sure. So NFPA 54 is kind of our rule book. It tells us what we can and can't do with venting, depending on the category, depending on various limitations, whatever it may be. ASHRAE is more of our how to get there. It's the how to do it book, right? How to size for pressure loss, how to size for theoretical draft, and the such. So those are the two primary things that we use as a company when it comes to sizing gas venting. We know what our limitations are based on NFPA 54, and then we know what the math is, what the calculations are based off of the ASHRAE handbook.
So when you're dealing with appliances, typically, one appliance, you can just size the vent, vent it outside. You're probably okay. A couple, you get like 2 or 3, and that's the thing. I mean, with especially when you think about it, when you're dealing with heating appliances, and this may not necessarily be the case down south, but in the northern climates, you're going to have redundancy. You're going to have multiple boilers to make sure that you have a backup. They might run at the same time, so you're going to end up putting them into the same header. That can be a little bit difficult and tricky, and I guess that's probably where draft inducers, the different types of products that you represent, come into play.
Correct, and I guess to kind of give some backstory. Yes, you're right. In the South, we don't have the heating load, but there are many times in the South, boilers are actually used, are put in a more difficult situation because they're using their boilers to heat up the room or heat up the building in the morning. But by lunchtime, they're shutting those boilers off and putting their air conditioning system online because, solar gain and such. So in Texas, there's several school systems where they'll run their boilers for 3 hours in the morning and then shut them down and then run the chillers to run the AC system. Typically in the North, you turn the boilers on and they just run until March or April or May. So it's actually in the South, it's kind of a misconception that boilers are actually more critical sizing in the South because they're used less. And what I mean by that is, as you said, you might put 2, 3, 4 boilers into a common stack, and the math adds up that common stack will work great when all 4 boilers are running. But if you're considering one of those as a redundant boiler, you've now oversized your stack by a third, and you figure that those 3 boilers were sized for the full, ASHRAE design day, which typically, is not every day of the year. So now you're maybe only running 2 of those boilers. But with turn down and rotations and all of that affects how your boilers are vented. And so even if the math shows that for example, 4 2 million BTU boilers will vent properly in this common stack because it's sized properly to NFPA, it's sized properly to ASHRAE, meets all of the requirements, but is it going to perform properly under all conditions? Whether it's a 5-to-1 turn down boiler, a 10-to-1 turn down boiler. Some of these larger boilers are now getting 20 and 25-to-1 turn downs. So you're sizing even individual boilers. You're sizing a boiler or a stack for 6 million BTUs individually, and that turn down goes down, 10-to-1. That's only 600,000 BTUs going up that stack. Will you have draft performance all the time? Maybe or maybe not. So that's where mechanical draft comes in. And the best thing about mechanical draft and the products we make and a couple of our competitors, it's all based on pressure. So we really aren't looking at, what the boiler firing rate is. We're not looking at the outdoor temperature versus, ambient versus fluid temperatures. All we're doing is trying to maintain a pressure. And typically on these, on the packaged boilers, that's what they're looking for as well. What kind of back pressure or what kind of negative pressure are we seeing at the outlet of the boiler? So we get into, whether it's a termination style fan or inline fans, it's all going through a master controller that's taking readings in the stack of pressure. And then we're just going to modulate that fan based on that pressure. As boilers turn on, that pressure is going to increase, start to approach positive. Our sensor will see that, ramp the fan up to decrease that pressure.
So I know, especially when I first learned about these, it was very much a fan that you put on the terminal on the end of the stack. What other varieties do you have of configurations?
Sure. So US Draft, we have two different types of inlines. We have a straight through and a 90-degree fan. So draft fan manufacturers are really starting to see, and the reason being is, again, 20, 30 years ago, we talked about pressures in stack. If you had an old Category 1 V-vent system and you wanted to put a fan on it, you couldn't use an inline fan without changing all of the stack downstream of that fan, because now it's positively pressured. So they would put a termination fan and just keep the entire stack negative. More and more with boilers using UL 1738, which is rated for pressure, it makes more sense from a maintenance standpoint and from an installation standpoint to try and keep everything in the mechanical room. So you can have your common, you can have your fan, you can have your drive, your controls, your sensors, everything is in that mechanical room, rather than maybe putting it up on a 3, 4, 10-story roof, having to run electrical, signal wire, all of that. So inline fans are really, I would say, a majority of our business. We still do a lot of termination fans because there are still a lot of older boilers out there that they want to use, their old V-vent system, for instance, or they just don't have the space in the mechanical room. But I would say a majority of our business is more of the inline type product.
Now, I guess what are some of the knocks against these draft inducers?
Well, the biggest pushback I always get is that it's a single fail point for the system. If you have 3, 4 boilers, again, we talk about redundancy, having an extra boiler in there. So if one goes down, you still have full load. But there's only one fan and there's only one controller. And so there's no redundancy. And my response is absolutely. That's a single fail point. If you put one fan and one controller, something were to happen, though we try and make the highest quality product we can, it's a mechanical piece of equipment and eventually it will, need to be repaired. So that was kind of the same argument 40 years ago when redundant pumps started coming into play, or that's how the modular boiler really started to become popular, is because you would have one large, fire tube or water tube type boiler with one large, full flow system pump. And if any component on either of those products went down, the whole system lost heat. So they started to put in these smaller multiple boilers so you could have that redundancy. And then engineers started saying, well, if we have redundant boilers, now we need redundant pumps. So instead of putting 2 large pumps, instead of putting one large pump, they'll put 2 slightly smaller pumps. One can handle 70% of the load, maybe 80% of the load. Or they'll put in, 200% full redundancy pumps. And for whatever reason, that mentality has not shifted into draft controls. Anytime we do medical facilities, hospitals, whatever, that's required. So we'll put 2 fans with 2 controllers, with a redundancy controller, and be able to fully automatically, just like the pumps, just like your boilers, automatically switch between systems. And so obviously there's added cost to that, and for whatever reason that just hasn't really taken hold. It's tough to explain because, again, when you walk into a mechanical room, you typically see two of everything, whether it's, again, boilers, pumps, sensors, that type of stuff. So that's really the biggest knock I get, and that's always been my response is, well, we can fix that and sort that out. But
it's just money.
It's just money, exactly. And of course, it's easy for me to say as the fan manufacturer trying to sell more fans, right? But in the grand scheme of the mechanical room, the draft, the mechanical draft systems maybe going to be 5, 8, maybe 10% of your project at most, even with a redundant system. You're not looking at adding, you're not doubling the mechanical room cost. You're adding some cost, no question about that. And there's a little bit more wiring, a little bit more install to it. But when you look at, and I always kind of chuckle when they say, well, it's adding $6,000 to the project. And I'm thinking, yeah, that's a $600,000 boiler room. So I've added 1% to your boiler room. And if there's not a 1% fluff in someone's numbers somewhere, then we got bigger budgeting issues than my mechanical draft system. So, there are definitely ways to do it, and we can be very creative with the designers to say, okay, we won't give you 100% redundancy. We'll size 2 fans for 60% of the load. And in an emergency, 1 fan goes down or 1 controller goes down, you'll have 60% of your boiler plant. Are you satisfied with that for the 4 hours or 8 hours or however long that they can be down? But if it's critical, like I said, hospitals, schools, sometimes industrial plants that say we must have our boilers online 24/7. Well, then buy redundant fans. That's the only way we can guarantee that.
Okay. Now, I know that there's a different product that's sneaking into your portfolio. They're called individual connector draft system. Can you tell us a little bit about that?
Sure. So we introduced the CDS about a year, 14 months ago now, last July, late July. And it's a concept that our engineers have been, I guess, working on for probably about 3 years prior. For the 35 plus years of mechanical draft here in the States, it's always been about the system. And for category 1 appliances and for even the high or the low turn down category 2 and 4, that will probably work very well. In most cases, it'll keep you within a range. But with these newer technology boilers that are very, very precise on their draft, well, let me restate that. Many boilers nowadays give you a range of what they can handle on their draft at the outlet. And every time you get something from a boiler manufacturer, they're saying, here's the pressures we want to see at the flue outlet of our boiler. They really don't care what's going on past that. They just want to know what's going on at their boiler. Now, granted, whatever's happening past that will affect what happens at their boiler. But that's what matters, is the flue outlet pressure. And a boiler manufacturer may say, hey, we can handle plus or minus 1/4 inch of pressure. And you think, okay, great, I've got a 1/2 inch swing in my flue system that I can work with. Do I stay within that 1/2 inch swing? Yes, I do. And then we green light the vent. What I would caution you on is that while they can handle that, most boiler manufacturers would not want to see that kind of a swing. If you can tell a boiler manufacturer or a startup tech or a commissioning agent that I can give you this pressure, and that pressure can be anywhere within their range. So we use that 1/4 inch, plus or minus 1/4 inch as an example. If I can say I'll set my controls at a 0.05 negative or a 0.05 positive in a common vent system, and I will always, under all conditions, set that or maintain that pressure. Now that boiler manufacturer commissioning agent can go in there and dial down their combustion into a more precise, a better combustion setup, so that it's more stable, more efficient, which then gives you your proper heat transfer, which then starts, to see those thermal efficiency numbers that they're publishing. And it will not only operate better, but then it'll be easier to maintain, because now you're not getting improper combustion. You're not getting overdraft. And overdraft on these newer premix mesh burners start creating pinholes in their burner, and those burners start to wear out very quickly. And so by putting the CDS, the connector draft system, an individual draft controller on each appliance, we are now maintaining draft at the boiler where it matters most. Now that common, if you do that individually, obviously size the individual stack to maintain what we call worst case scenario, and then we kind of start to use the damper to choke that off. If it's in a common vent system, we size the common for that worst case scenario and allow the damper to control. But now it's controlling at the boiler. And that's really what matters to these 93, 95, 98% efficient boilers, is that we start to trim that. We take that half an inch range and we choke it down to 2/100 of an inch. So I'm going to maintain my set point of a 0.05 negative. I'm going to maintain 0.04 to 0.06, 365 days a year. So if my draft is affected by outdoor temperature, doesn't matter to me because I'm going to maintain that with the damper. Firing rate doesn't matter. I'm going to maintain it with the damper. And to me, it's taking that technology of, again, to analogize from back in the day, you had one big boiler with one big pump, and it was a full flow system, and whatever the system needed, that's what the boiler got. Well, as we went into modular boilers and these smaller type boilers, they had a very specific flow rate. So to maintain that very specific flow rate, you put a primary secondary system in where the boilers had their own primary pumps. The system had a secondary pump. So the system pumps did the system, the boiler pumps did the boiler. That's pretty much what we're doing with this. We can have a mechanical draft system to do the system, to do the common, and then we have a CDS, the connector draft system, working on just for the boiler. And it really allows us a lot of creativity and a lot more flexibility on our venting systems. We have several systems nowadays that they're doing the common vent natural, and it will, under most conditions, be a negative. And so we'll set it for a slight negative, or we'll set it for a slight positive at the boiler. But there are times that stack can go positive. And in that scenario, we have the positive shut off. So if the boiler's not running, it's positively shut it off to the rest of the system. And it really allows a much better control of your draft, which again, to me, I've been taught this from the time I was introduced in the industry by my father and from others, but he instilled in me that 90% of your boiler issues are venting related. So if I can eliminate 90% of your boiler issues with a simple device, I think that's a pretty good ratio.
So when you talk about 90%, let's talk about some of the issues that you can have with improper venting. I mean, what would you see?
So if you have too much draft, that's where we get into the flame pulling off the burner. You're literally pulling most of the mesh head burners. The flame is anywhere from a half an inch to an inch and a half, I guess, height to the flame, but the base of the flame is right on or just off the mesh. When you start to pull that flame away, where it's not igniting until it's off the burner, now you start getting hot spots on your burner, which then start to crack and cause issues on the burner. If you don't have enough draft, now you start to soot. You have incomplete combustion because you're not getting enough air transferring through that heat exchanger, so it starts to soot up, and then it starts to cake onto the heating surface, which then becomes an insulator, which then means you don't get your proper heat transfer. So there's, excuse me, there are so many, and those are the two main things. It has to do with combustion, right? If I can't get the flue gases out properly, it's going to affect how I burn. And if you took your car and restricted your muffler, or restricted your exhaust pipe, your motor's not going to run properly. If you are overcharging it with too much pull, it's not going to get enough proper combustion. So it's really about maintaining that combustion, giving it the time to mix in the combustion box, igniting off the burner, maintaining heat transfer properly through the appliance, and then out the stack.
So I know that there's different advantages that you can use these draft inducers for. Mm-hmm. Say, for instance, you had a boiler stack that was not the right height off of the roof, Can you make up for? I mean, how are some of the applications that you can kind of maybe make an architect happy? Not that that's your entire job, but how could you make an architect happy by using a draft inducer?
Yeah, absolutely. So the many of the codes that are written, and that being one of them, typically, so there's a reference in the code book about the height of your stack, how tall your stack has to be, and depending on the situation, it's anywhere from 2 to 3 feet above anything within 10 feet. So if you're within 10 feet of a parapet wall, for instance, you have to be 2 feet above the parapet, but 3 feet above the roof. Pitched roof, same thing. You have to go out 10 feet and clear it by 2 to 3 feet, depending on the situation. Within that code, it also states, it must do this, or this, or be an engineered system. When you start to use mechanical draft systems, we are considered an engineered system. So as a designer, you say, hey, my stack has to clear this wall by 3 feet. But I don't want to see that from the street level, because the architect or the owner of the building doesn't want to see stacks protruding out their building. They can put a mechanical draft fan on that and overcome that. Same thing with oversized stacks. There's the 7 times area rule. So basically your smallest vent, let me restate that. Your largest vent, the area of your largest vent cannot exceed the area of your smallest vent by more than 7 times. This is a big problem in schools that were built in the 50s and 60s. Had one big boiler with a 24 or 28 or 32 inch chimney, and then they decide that they're going to go down to smaller boilers that can be dumped into that chimney, and a little 40-gallon water heater, and the boilers might make it, but that water heater never will draft. And the reason being is you can't heat up the stack enough to get natural draft through that that little water heater. So we put a mechanical draft fan on it, and it now is mechanically inducing that draft through that stack. Combining categories. You're not allowed by code. You're not allowed to put a category 1 and category 4 boiler in the same stack, because of pressure differences and corrosion, but more so for the pressures. And so you put a mechanical fan on it. It's now an engineered system. So we can now start to combine products. So again, it gives you as a designer, whether it's for architectural or limitations. If the owner says, hey, we just replaced our roof and we can't cut a hole in it, and so you have one hole to put these 4 different appliances in, good luck. That's what they tell you. Here's your limitations, now go. And you look at it and say, well, I can't put this category 1 water heater that's sitting here in with my new category 4 boilers. So I either need a new hole or I need a draft fan. Those are the 3 biggest ones that we see when it comes to code, overcoming code issues with mechanical draft.
So I guess kind of wrapping up a little bit, is there any advice that you can give for anyone listening, any designers out there that they should consider, or any tips when they're actually designing vent systems?
What I've always told my contractors and engineers is that venting should always be the first thing that you look at. Everyone, typically when a boiler is selected, they look at the efficiencies. Maybe they'll look at the turn down ratio. Maybe they'll look at their water design, their design system. Okay, we're going to do a snow melt system or a radiant system where it's going to be a low temp system, so we can use condensing and we're going to really soak up some of that energy, and that's fantastic. But if you can't vent that boiler properly, you'll never be able to get the efficiency numbers they're looking at. So many times from a design standpoint, just look at your venting first. That's what I would look at first. Is you say, we're looking at this type of a product. Can I vent that product? If that answer is yes, great. Now we can get into how do we pipe it? How do we get gas to it? How do we get electric to it? Because typically, most systems using primary, secondary, that boiler pump can overcome a couple extra fittings. And I tell the contractors the same thing. If you're going to install that boiler, set the boiler and at least stub out the beginning of your vent, natural or mechanically. Just come out and go up and get above where all of that mess is. Most of these boilers have everything on the back, which is very real nice for a final install. but it limits you on what you can and can't do with certain things. And if you've run your water pipe and you've run your gas pipe and you've dropped your electrical conduit, and now you have to get a 10, 12, 14-inch flue through all of that, much more difficult than if you come out with your 14-inch flue and then try and figure out how to use your 2-inch piping or 2.5-inch pipe around that. So to me, venting should be the first thing you look at in all circumstances for any gas-fired appliances.
All right, fantastic. So if any of our listeners out there want to learn more about venting, where can they go?
Sure. So our website is www.usdraftco.com. So usdraftco.com. All of our products, all of our many discussions about the things that we talked about today has our contact list there, and they can get a hold of me, and we can direct them to their local representatives. ASHRAE is a great resource. The code books are really starting to get up to date. They're really starting to refine for categories 2 and 4. But best source is to check out our website, get a hold of us, and we can take a look at your system and determine, whether or not a mechanical draft is going to be helpful.
All right. Well, I appreciate your time, Jason, talking about boiler venting.
Thank you, Matt. Appreciate it.
All right. Thanks again to Jason Geagan for taking the time to chat with us. Check out show notes for some of the links that we mentioned too in the show, and also his presentation. I snuck a link to our local ASHRAE website so you can take a look at what the presentation looked like. If some of these graphs and some of the things we talked about didn't really make audio sense to you, if you need to actually look at some of these things. But it's a really good resource. So check it out. Go to HVAC360.com/102 for the 102nd episode. All right. Well, thanks so much for listening. Hope this was helpful. If you know somebody looking for more information on boiler venting, why don't you go ahead and share this episode with them? If you're not a subscriber, again, consider going over to the growing community of HVAC enthusiasts. I don't know why I'm saying enthusiasts, but enthusiasts, people who love HVAC, who want to learn more, who want to be in a community that it's just about growing and learning. So go to HVAC360.com, sign up for that mailing list right there, and become part of that. Lastly, if you want to make a review, I would be deeply honored if you give me a review on Apple Podcast or wherever you listen to the podcast. I would greatly appreciate that, and I'll even give you a shout out on the next show once I know that it's there. So, all right. Well, that's a wrap for this week. And this episode of HVAC 360, I'm Matt Nelson, helping you be the best and the brightest in the field of HVAC. And as always, know what you build and share what you know.